testing to underground, which is why there are no more above ground tests. The threshold test ban treaty here, it bans nuclear weapons testing above a yield of 150 kilotons. And then here in 1996 is the Comprehensive Nuclear Test Ban Treaty. And this is the treaty that really drives my research. And so the Comprehensive Nuclear Test Ban Treaty bans all nuclear weapons testing worldwide. This is an actual picture of the treaty signed by Bill Clinton in 1996. It has not gone into enforcement for various reasons, but nonetheless, we are still trying to build up a verification regime around the world so that when it does go into enforcement, we have the tools and capabilities to monitor. So I focus primarily on seismic discrimination, which is sort of one niche of nuclear explosion monitoring. So in the case of the CTBT, what we're really trying to tell is the difference between earthquakes and explosions. So, you know, I have a picture here of a really large earthquake. It has surface expression. And then we have a mushroom cloud explosion. But in reality, it's really not that simple. Most earthquakes are occurring underground and do not have any surface expression. And as we learned from the limited test ban treaty, we no longer have above ground nuclear explosions. And so we've been developing discriminants since the 1960s. And it was actually a very large field of study in the 1960s. And these older discriminants focused on really large seismic events that were recorded really far away. And the reason for this is because, you know, with the technology at the time, seismometers were not really densely globally distributed, right? And so you have to have a big event that is able to be recorded at far distances. So I just want to highlight this discriminant right here. This is the ratio of body wave magnitude to surface wave magnitude. That is not really important. What I want to highlight is that this is a screening line. And so a screening line helps you screen out non-nuclear events. And so these sort of bigger circles are nuclear explosions. The gray small dots are earthquakes. And what we want to do is come up with a line that separates the two populations. And then, you know, for a fun fact, I've highlighted here in red, they've revised the screening line back in 2012 because of the North Korean nuclear explosions were too close to the original screening line. But so just keep that in mind because that is an area that I'm going to talk about in a little bit. So the newer discriminants are focused on small events recorded at close distances, what we call local distances. And this is actually a much more difficult problem because at these close distances, you're a lot more susceptible to the geology that the seismic wave is traveling through. And these are just a couple of sort of what the newer discriminants. This one is trying to extend old discriminants to these small events at close distances. Doesn't really work. And then this one is trying to do depth discrimination. And so depth discrimination is the idea that there is a limit in anthropogenic activity in terms of depth from the surface. So this drawing is not to scale at all, but you can sort of think of most human activity occurring in this sort of yellow box, right? And that's just based off of our technological capabilities. And so the idea is that if you have an event occurring down here, it's probably not anthropogenic, it's probably not a nuclear explosion, you can just screen it out. And the idea of screening it out is you're reducing work on analysts who are actually having to look through this data every day. And so moving forward, I just want to give a brief disclaimer that I'm using chemical explosions as analogs for nuclear explosions because there's very limited nuclear explosion seismic data. So most of these explosions are quarry blasts, but we also have a population of explosions that are rocket motor detonations out in the desert of Utah. Okay, so getting back to what ML and MC are. So if you're looking at a seismogram, you can think of them as a function of some sort of ground motion over time. And so you're looking at that. This is an earthquake, by the way. And you can say, okay, well, what is the maximum amplitude here? And you can plug that into this equation developed in 1935 to get a local magnitude. So this is Richter magnitude, what you commonly see reported in the news. But there's many different ways to measure magnitude. And so another one we're looking at is coda duration magnitude, coda magnitude. It goes by many names. And that is the duration of the seismogram. So from the first arrival here to where the seismogram ends. And you plug this duration into the MC equation. And again, we get a magnitude. And the idea of magnitudes is that they're representing some objective event size, right? You want them to be the same because there's ideally only one size for any seismic event. So it's really interesting when you see a systematic difference. Little differences are actually very common, but systematic differences, you need to investigate that a little bit more. So I want to highlight this figure here on the left. It's showing ML minus MC values, so the difference between the two magnitude scales, and then they're just histograms. And we have all events outside of mining areas and events within mining areas. So events within mining areas are all shallow, okay? And so they actually, we found, have negative ML minus MC values, which is, again, not what we want, versus events outside of mining areas, which are deeper events, and they have roughly 0 ML minus MC. This is what we want. And so we've developed a depth discriminant based off of this ML minus MC, with the idea of if there's a large difference between the two magnitude scales, it's likely closer to the surface, shallow, warrants further investigation. And so, the first step is being able to show that it works outside of Utah, right? And outside of a certain amount or certain type of event. So over here on the left, I'm showing that it increases with depth. ML minus MC increases with depth for earthquakes in the entire country of Italy, induced earthquakes in northern Oklahoma and southern Kansas, and volcanic earthquakes in Yellowstone National Park, in addition to Utah, using the data that I showed on the previous slide. Over here is ML minus MC for earthquake and explosion populations. And keep in mind, ML minus MC is not a source discriminant, right? We're not saying this is an earthquake or an explosion, but what we're doing is we're taking advantage of the fact that explosions are shallow and earthquakes are deep. And so we were able to show that the two populations separated in Wyoming, in the state of Washington, and in Nevada. So there are further sort of research goals, right? So now that we've established, okay, this works, it trends with depth. So how do we optimize it? How do we get the best performance that we possibly can out of it? And so there are 3 main research questions. What is the relationship of MLMC with geographic distance? And what that means is between the event and the seismometer that recorded it, how does that distance affect the MLMC ratio? The next is, what is the best screening line? And so think back to what I showed, separating the earthquakes and explosions. We're trying to come up with the screening line that best separates the two populations. And then lastly, do different formulations of ML and MC perform better? I showed the original equations. Those are based in physics. They were developed quite some time ago. Can we change those the coefficients of those equations to have better population separation? So we're starting on a catalog in Utah. It consists of about 1,500 earthquakes, mining-induced events, and explosions. So here on the left is showing each of these sources. The explosions are shown in the green crosses, earthquakes are the purple dots, and mining events are in the orange squares. But again, it's not a source discriminant, it's a depth discriminant. So we choose a depth threshold of 5 kilometers below the surface, and we split the catalog up. And so the blue events are shallow, and the green events are deep. And then just as a side note, the explosion catalog was carefully and meticulously curated by an undergraduate student that I supervise. So I really have to give him the credit. And if you would like to use this in your research, it's available upon request at the University of Utah. Okay, so let's start with how do we calculate mlmc. If you recall, I talked about how you have to measure amplitude and duration for these magnitude measurements. The issue is that we need more data than the analyst can provide in the original earthquake catalog, because there's a limit to how many amplitudes and durations that they can really measure. And so we came up with an automated method to measure amplitude and duration. And these are just examples of an amplitude measurement, of a duration measurement for an earthquake in Yellowstone National Park. And then just as a reminder, these are the equations for amplitude and duration. And again, if you want to use this in your research, it's available on GitHub. It's called MadPy. Okay, so before we can move forward, we need to do quality control. We need to make sure that this is consistent with the catalog local magnitude and coded magnitude values. So if you look on the left, we have the shallow vents on top, deep events on bottom, and histograms of ml-mc values. We have the shallow events with a pretty negative mean, whereas the deeper events have a mean of about 0. Again, that's showing exactly what we expected and exactly what we've observed previously. And we compare that to the, I call this the USS catalog. This is essentially just the earthquake catalog that we were originally looking at. And one of the ways that we measure the separation between the two distributions is a term called Hellinger Distance, not to be confused with Geographic Distance. The Hellinger Distance just measures how separate these histograms are from each other. So if the Hellinger Distance is 0, that means that the histograms completely overlap. If the Hellinger Distance is 1, that means they are completely separate and do not overlap at all. And here we have Hellinger Distance of 0.416 and 0.42. Which is not only a good Hellinger distance, but also shows that we can move forward because the automated measurements are as good as the catalog. So getting to this first question, what is the relationship with geographic distance? So we can look at this manually, right? We can see how it varies with distance, and we can also look at it this way. But what we really are trying to get at is, can you use distance as a metric to classify whether an event is shallow or deep? And so what we do is we take distance and we take the mlmc value, the ml-mc value, and we say, okay, let's put it into this machine learning model and let's see if we can classify it as shallow or deep. And it turns out we can, and we can do it pretty well. But the issue is that we cannot do it well with individual stations. So individual stations, I guess the data is too messy, there's too much variation. But once you event average those, so once you take the ml-mc values, or I'm sorry, the probabilities that come out of it, and you average them for each event, suddenly you get a really strong performance. And so right now we're looking at a confusion matrix, because it's confusing to look at. And we have actual classification, so if it's shallow or deep, and the predicted classification, shallow or deep. And so if you look here on this diagonal, these are the correctly classified events. And then on this diagonal, these are misclassified events. And what you want is more events that are correctly classified. And that's what we have shown here. This is great. And it's a really important result because it says, okay, we need to event average. This is not a single station method. And also the geographic distance is a vital component. The next question is, what is the best screening line? As I was describing earlier, if we plot ML and MC and we plot the deep and shallow populations, what is the best line that separates those populations? So we tried two methods. One of them is a brute force grid search. So that's just sweeping the line across as many combinations of slope and intercept that you can. And then another one is, again, another machine learning model called Logistic Regression. And again, this is a classification regime, right? So we're plotting the line and we're saying anything above the line is shallow with a bigger MC, and anything below the line is deeper with an MLMC of roughly 0. And so these are the results here. We have ML here, MC here. We have our 2 lines, or technically we have 3 lines. One of the lines is from a previous study. And we're getting pretty good performance out of the new data. The previous study is not doing so great. So you can think of this as sort of like an accuracy. So here we're doing 67%, not really that great. Here we're doing about 85%, a lot better. But we really want to translate this into a real world application, right? So we have a great screening line, that's great, but what does that mean? That means that we can reduce the analyst workload by 21%, which for a catalog of roughly 4,500 events may not seem that large, but if this holds true for a catalog of 1 million events, a workload reduction of 21% is quite large. So this is a really encouraging and promising result. And lastly, do different formulations of ML and MC work. So here, I've substituted out the ML equation in favor of a parametric version. The previous version was not parametric. This is the same code of magnitude equation here. So if you take ML minus MC, this is the equation that you get. I'm going to call this equation with these coefficients the base equation, right? This is what we're getting now. And then we search through different coefficients. It's a 4-dimensional brute force grid search of each of these coefficients for the equation. And we remove this bias term because all it's doing is shifting this histograms from left to right. It's not actually contributing to the separation of the populations. And we find that the current formulations are optimal. So this is our search space from -3 to 3. And then this is each parameter coefficient and its associated term up here on top. So the base coefficients, which is this dotted line here, it leads to a Hellinger distance of 0.495. And when you grid search and you find the highest Hellinger distance, which is shown by the solid line, you get a Hellinger distance of 0.5. So you really haven't improved this much. And this is a really important result because it's saying that our current definitions are not only optimal for discrimination, but also that they are generalizable because they're constrained by the physics of the problem and not by the coefficients of the equation. And so if you remember, I had talked about that there was a depth threshold of 5 kilometers that was chosen in a completely arbitrary manner. So the last portion of this research, this particular research project is, well, what happens if you change that depth threshold? And so we vary the depth threshold from 0 to 10. And we have significantly poor performance, basically at a depth threshold of 3 kilometers below sea level. So really the optimal depth threshold is about 4 kilometers for every single test. And then this is just a little sneak peek at a project that's still, that's in its earlier stages. So a group out of Lawrence Livermore National Lab, they digitized nuclear explosion data that was recorded at what is previously known as the Nevada test site, and they made it publicly available. And so what we're trying to do is apply MLMC to these nuclear explosions. This is a lot more a difficult problem because these explosions are large and they are recorded at far distances. And so we don't really expect the performance to be as good as it was for that Utah catalog, but this is still a work in progress. So, you know, what is this for? Why are we doing this? Because we're trying to sustain the geopolitical climate. I think a lot of us are aware of what's happening right now in Ukraine and Russia, right? We don't want these situations to happen, and we don't want to be concerned that other countries are developing nuclear weapons. And lastly, there have been many funding sources for this research. The Department of Energy. So basically, these are the primary research labs that I've collaborated with, but there are many more national labs that are doing this research. The Air Force is a very big funder of nuclear explosions monitoring via seismology. The Army Corps of Engineers is also very interested in this because they use seismic data to track troop movement. And so this is what they are primarily interested. And then lastly, the USGS, which is typically sort of an earthquake agency, they're interested in this because if you can screen out mining events, you've reduced their analyst work, right? Because all they care about are explosions or earthquakes. So now I'm going to talk about other research that I've done. And it's quite a lot of research. So I'm actually only going to talk about or highlight two regions that I think sort of give an idea of the breadth of research that I do. So the first one I'm going to talk about is induced seismicity. So this is a problem that I've been working on for several years now, and it's seismicity induced by wastewater injection. And it can generate some pretty large earthquakes. And so I think there are a lot of people that say, okay, well, the energy industry should be stopped and induced earthquakes are bad. But the truth of the matter is we are completely reliant on the energy industry. This is how our society functions. And so what we really need to do is figure out this trade-off between human safety and resource extraction, because there is a fine line there, and we're still trying to figure that line out. And then I would also say, you know, geothermal energy is the next big thing, right? But geothermal energy can also induce earthquakes. So this is a picture right here of Forge. It's a multi-million-dollar Department of Energy project in the desert of Utah. And this project is to monitor induced or seismicity before, during, and after the well activity. But there's another aspect to induced seismicity that I don't think a lot of people have really thought about, and this is municipal water management. So in the Chesapeake Bay of Virginia, they are really struggling with aquifer depletion. They are losing their drinking water. And so what they're trying to do is come up with a closed system where they take the wastewater, they treat it, and they inject it back into their aquifer. The problem is when you inject water into the earth, you get induced seismicity. And so this is a project that I'm on, and I'm sort of the seismology expert collaborating with the hydrogeologists of, again, monitoring these wells before they come online, while they come online, and after they come online to see what this effect is, if this is a sustainable method, because if it is, it can be used around the world. And now I am completely switching gears to isotope geochemistry. And I am not an isotope geochemist at all in any way. But this research was going on in my department at the University of Utah. So this is the idea that the ratio of strontium 86 to 87 can help track where elephants come from, right? Because it goes into the water, into the soils, the elephant eats it, and it gets into the tusks. And so the idea is, okay, well, if I seize a tusk at customs, can I trace back to where that elephant came from and sort of who or what groups were poaching it? And so this is just sort of showing, like, in each polygon, they divided this area of Eastern Africa into polygons, sort of what the isotope ratio that you can get. My part in this was doing the math, doing the least squares inversion, because this is something that they they were, they came to me, they said, we need a method to figure this out. We have this data, we're not really quite sure what to do. So I said, well, at least where's regression will help you, weight some parameters, and this will really help you. So hopefully this will be published soon. And then I want to talk about big sort of questions in seismology that have really captured my attention. So the first is, what is the seismogram? Is it mostly the path or is it mostly the source? So we know that seismograms are a combination of how the Earth slipped and the geology that it traveled through. But what we don't know is how much of each is in the seismogram. We know that the further you get, the more you filter out the effect of the geology, but that's really about it. So I first came to this project with the idea of, this is the work I did with the Air Force, with the idea of, can you hide a nuke in an aftershock sequence? Because if a seismogram is mostly path, then theoretically you could, and actually they're finding examples where you might be able to, essentially. But this has really broad implications the more that you think about it, just in seismology, because so much of what we do is based off of this assumption that if waveforms are similar, they have the same source and the same path. Another really big question is, what sort of rheologic conditions do you need to create and generate earthquakes? And so this was a project that I got introduced to at University of Utah. Primarily because they are the network that monitors activity both here in Utah, but also up here in Yellowstone National Park. So they have access to a lot of this really great data. And so, there are earthquakes that are happening at 80 kilometers depth. They're 30 kilometers below the Moho. And no one really knows why. This is a really big question. They shouldn't be nucleating down there, not when they are in the mantle. And there's been a few arguments. Some say, it actually really is cold and brittle. It's from, the remnants of a subducting plate. And others are like, oh, actually it's like warm and ductile, and this is kind of weird. And so this is a project that's really been on the back burner that I want to bring to the forefront, because the University of Utah has actually reported a lot more deep earthquakes that haven't been published, in addition to they had analog records of these deep earthquakes from the 70s that also have not been published. All right, so now I'm going to get into my research on diversity, equity, justice, and inclusion. So I just want to briefly talk about what is diversity, equity, justice, and inclusion. So diversity is multiple backgrounds and perspectives. Equity is ensuring that everyone has the tools that they need to succeed. Justice is, let's remove those systemic barriers to success. And inclusion is, let's create a system for everybody. It can also mean, let's have an overall sense of belonging for everybody. And I am going to refer to it as DEGI moving forward, because it's easier to say. So I think diversity and inclusion are pretty intuitive, but I think a lot of people are sort of like, well, what is equity and justice? And so I really love this graphic for that demonstration. So this is inequality. The tree is bent this way. This person's getting apples. This person is not getting any apples. And when you implement equality, you give them the same size ladder. But again, the tree is bent this way. This person is still getting more apples than the other person. Equity is, okay, well, let's give this person the taller ladder so that they can reach just as many apples as the other person. But justice is straightening the tree, right? Let's fix the entire system so that we can have equality, so that equality works and offers the same opportunities for everybody. So, before I get into this, you might be like, who the heck are you to tell us about DEGI? And I just have a ton of experience. I've been doing research in this for years. I've talked about it a lot. I've participated in a lot. So please trust me when I say that I'm somewhat of a subject matter expert in this. So DEGI is sort of incorporated in everything that we do. So these are sort of implications for research here. Seismic vulnerability, what people of a lower socioeconomic status tend to be more vulnerable to events. We had a large earthquake in Utah. It's people in the mobile homes that really were harmed a lot more than other structures. Data ownership, if you add something to someone's land, who owns that data, right? If I put a seismometer on someone's land, do I own the data? Do they own the data? And this has been a really big problem, particularly in native populations, but just in general. This picture is from an issue that's happening in Chicago right now. Policy decisions. Policy decisions have typically been made by one demographic, but science has shown that when you have a diverse group of scientists, you actually make a lot better scientific decisions. You have stronger scientific research. And then lastly, resource accessibility. Let's say you want to go out into the field. Do you have the financial resources to buy the tent, the hiking boots, all of that, right? Do you have the vans to carry everybody? And this is pretty inequitable. The larger research institutions do have these resources, so they can do this research. The smaller institutions don't, so they can't do the research, therefore they stay small. So what I bring to this is, first of all, I bring a completely different background than has historically made these policy decisions, right? And so that sort of helps, again, with this decision making. And I've also communicated science a lot and effectively, and I care about this, and that increases public trust in the science. And this is really, really important, I think, as we've all seen with COVID-19. So there are other considerations with teaching. So, I think, first of all, a syllabus it's essentially a contract between the students and the faculty, and it outlines the expectations, right, of a student. And I think many faculty know this, but I'm not sure that many students know this. And I think it's really important that it's explicitly stated that this is an outline of expectations, because then students can really understand what is expected of them, how to go about doing certain things, etc. Additionally, add campus resources to your syllabi. A lot of students, especially the ones who are struggling, are not likely to do the work to go seek out the help, because it's a lot of work. And so just something so simple as adding these links, these resources in the syllabus can go a long way towards helping students feel supported. Make sure your course content is relevant, right? If I'm deriving the wave equation, someone may not understand why I'm deriving the wave equation, but if I say, no, I derived this because it travels through the earth and it might tell us the difference between an explosion and an earthquake, that's a lot more exciting, right? Because I'm like, this is the basic blocks and we build on it. And lastly, just the true origins of the material. And I think this particular example is changing. But back when I was an undergrad, I learned that the first seismometer was, somewhere in Europe, I can't remember what, but actually the first seismometer was in China, right? And I think that's really important to not have Eurocentric, to actively combat Eurocentric ideas of where technology came from. And so I contribute in this way because when I teach, when I have taught, I communicate my excitement and my passion, right? Because when you communicate that gets everybody else excited, right? Because they're like, oh, okay, this isn't boring. This person doesn't think it's boring, right? And then also, I incorporate material that's relevant and exciting to students. Let's say if we're learning about seismology, I'll say, hey, did you hear about that eruption, right? That volcanic eruption. This is why we're doing this. And I think that also sort of increases attention. And lastly, there are considerations in mentoring. So first, expectations contracts. So the mentoring literature has said that it is very important to have an expectations contract between advisor and advisee. So things like, how many hours do I expect you to work? What are your requirements for graduation? Things like that is really important to lay out so that everybody is on the same page and there are no surprises. Another, again, campus resources, right? I think everybody struggles at some point. Ethical research practices. So I'm going to provide an example that I think is more modern than other people would provide. make your data and your code publicly available. This is the way that the world is going. We really have what people are terming a reproducibility crisis in science. And if you are conducting research that you are proud of and that you believe in, you should really be sharing it with other people and letting them have the data as well, provided it's not under embargo and such. And then, oh, I see a typo, unhide the hidden curriculum. So there's this idea of the hidden curriculum where you say, where people don't know how to navigate academia and there are things that people don't explicitly say, and that might hold some people back. So I put an example here. In 2016, I emailed somebody saying, I want to work in your PhD program. And that's because I have really strong mentors who said, this is how you get into graduate school. Graduate schools do not often accept cold applications. You need to often contact the advisor. And effective mentorship, right, is saying that explicitly, helping your students do these things. And so, you know, what do I bring? Well, first of all, I allow my students to explore multiple aspects of earth science, right? I've shown that I'm a collaborator, and students should have ownership of what they are doing, and they should be able to say, oh, well, this is interesting, but could I tie it to this? Yes, absolutely. I can learn from you, you learn from me. This relationship has reciprocity. Also, give my students the tools and connections to get jobs after graduation, right? Because ultimately, everyone wants a job. You know, most people need a job. And it's important to focus our content to make sure that students have the skills to be employable, right? And I have tons of connections with the national labs and with the USGS and networks all over the country and frankly all over the world. And because of these connections, I know what students need to get jobs there. And this is a really big one. I think a lot of the times when people talk about DEGI, they talk about cultural climate. How do we change the climate of our department, of our organization, et cetera? And what really matters is giving people the tools to transform the climate. So a lot of the times we use resilience as a positive term, right? These people are resilient, this is great. And it is a positive thing, right? But also what it means, the implicit meaning behind it is that they need to adapt to the system, right? That there is no changing the system, you're adapting to the system. It's perseverance, right? You're just having to go through it. And transformative resilience changes that. Transformative resilience gives people the tools to say, I need this, can you help me? And then someone else saying, yes, I can help you. We can work together to figure out a way to meet in the middle. So this is a summary of sort of what I want y'all to take away from this talk about me. So first, I'm a seismologist. All of my research is directly applicable to current societal problems. This is really where I intentionally focus my research on because I love that science can really help further humanity. I have done a lot of things. I've done research, I've collaborated, I've mentored several students, and I'm really big into DEGI, and I've been a vocal proponent of DEGI. You know, and if I were to be able to come to UTD, I would continue my work, right? And sustaining human resilience, right? We can't stop earthquakes, right? And so how do we build back? How do we sort of bounce back? And, you know, inspire the next generation of geoscientists, because ultimately what we're doing here is we are creating and curating knowledge for the people who come after us. And that's all I have. So thank you for listening.
Thank you, Lori. So we'll alternate between in the room questions and online questions. And for the online people, you might need to repeat the question when you answer it. So, is there a question from inside the room? Start off.
Yeah, a general question. So in your, you had to have event average measures.
Mhm.
Does that mean imperfections in the velocity model as a source of or the need for that averaging, or noise at the seismometer?
Yeah, so the question is, why do we do the event, or what is the physical reason behind the event averaging? Yeah, and it likely is, the velocity model, there's a lot of noise in that. There's a lot of noise in the amplitude measurements. There's a lot of the noise in sort of the calibration of the equation. So yeah, there's many sources of noise.
So that deep earthquake in Utah interested me because I tell my tectonics class that generally speaking, earthquakes are shallow, and the only time they get deep is in subduction zones.
Right.
80 kilometers beneath Utah, that would be at the base of the lithosphere. So that's a very unusual place. Why haven't we heard about this before?
It's interesting. There are, the question is, why is there so little attention paid to these deep earthquakes? And this is really interesting, but the more you dive into it, the more you actually realize that there's been a significant amount of research on it. But for some reason, it's not the research that's picking up notoriety. But there have been like 2 science papers, several BSSA, SRL papers, and it's really interesting because I had also never heard of it before, going to Utah. And then, it's something that only a few people are really picking up.
Can I have a quick follow-up on that? Do you happen to know what the uncertainty ellipse is in terms of what's the depth uncertainty?
So I don't remember what the depth uncertainty is, but I can tell you that there have been 3 publications that have, in different methods, confirmed the depth. I don't remember what the exact amount of kilometers, but it's 30 kilometers below the MOHO, and I don't think that the depth uncertainty reaches, I've never seen that the depth uncertainty reaches 30 kilometers.
Yeah, I mean, what's interesting, a lot of people don't pay too much attention to the uncertainty ellipses, and then when you start looking at the network and which events are being used to constrain it, sometimes they can be very elongated, the uncertainty.
Right, so the first 3, 4 publications were just focused on proving that it was at depth.
Great.
Yeah.
Let's see, let's go to online. Saloa, do we have any questions online?
No questions.
Not yet. Okay, then we'll bounce back while they're thinking. Yes.
If given the opportunity, what kind of classes would you want to teach, like specific class, and then also for DEGI, like what kind of activities would you make to foster that here?
Yeah, so the question is what classes I would like to teach and how would I foster DEGI in the environment. So one class I would be really excited to teach would be geosciences and pop culture, right? Because I think that's a really great class for non-majors to get excited about geoscience. How accurate was Paul Giamatti in San Andreas, right? Like what was Don't Look Up about? Things like that. I would also like to teach computer methods as an undergraduate level. I think as geophysicists, we get a lot of computational exposure, especially with the math courses. But I think a lot of the core earth science geology courses maybe don't have as much computation, but I also think that the way the world is moving, we need computational literacy to get jobs. And so that's something that I would also really believe in. And in terms of fostering DEGI, I've heard that Geo Club is very active, and that's community building is a really big part of DEGI. And so I would actually try to be really involved and build that up even more and perhaps do some other things. And I think also for anyone who's interested, I would love to sort of help with science communication and get people exposed to how do you communicate your message without being inflammatory and without being misunderstood.
I've got a follow-up question on that, if I may. So, and it's around field work.
Okay.
And JEDI. I use the acronym JEDI. So I've been on the board of directors of the Society of Exploration Geophysics for a number of years. And also, John Ferguson and I participated in SAGE, the Summer of Geophysics. In fact, John was a co-founder of it for many years. And so there's a lot of issues, which I'm sure you're aware of with, in our sciences, we often have a lot of remote field work, both in teaching, you know, in university courses, but also in jobs. And so if you did happen to come to UT Dallas, can you talk a little bit about how you might be involved in field work and in particular helping to address some of these JEDI issues?
Yeah.
For underrepresented minorities, et cetera, in fieldwork situations?
Yeah, absolutely. So the question is how to incorporate DEGI into fieldwork, essentially, if I were to come to UTD. First and foremost, and I'm not sure if this already exists, but there needs to be a fieldwork code of conduct. And these are really difficult, surprisingly difficult to formulate because there's a lot of back and forth and there's a lot of, well, maybe this happens, maybe this happens. But that would be something I would try to get on right away. Another thing that seems sort of simple, but actually does not exist in most institutions that I've been at is have a roster. Have a roster for who's going into the field. So I've heard many, many stories of people being left behind. And it's because they didn't notice, oh, you know, there's 20 people. I didn't realize that we had one person missing. We need to train, a lot of the times TAs lead field experiments, and we need to train TAs in how to handle difficult situations, right? And even professors, right? How do you, if someone comes up to you and says, this incident happened, I no longer feel safe, how do you handle that, right? And so you really would need to collaborate with social scientists really to understand how to deal with that and you need to collaborate with, you know, because you need to think of the logistics of that. Do we have to fly them out? Do we need to send them back? Like, what are we doing? Yeah, so there are many aspects, I think, to fieldwork that many approaches that you could take. And if I were to come here, I think first I would need to observe how fieldwork works before I could make a concrete plan, but I would make a concrete plan and then attack it one at a time.
Okay, thanks. So Lola, do we have anything online?
Yeah, we have a question from David. David, do you want to ask it? I'm not sure if your mic got fixed.
Yeah, sure.
Okay.
You all hear me okay?
Yeah, sounds good.
Okay, cool. So great presentation, and I like all the different diverse areas that you're talking to. And you did speak really lucidly about the different, you know, collaborations you've done with federal or international agencies and at different academic institutions. I was kind of curious if you could talk a little bit about the kinds of collaborations you'd like to pursue with industry, especially given that DFW is such a, you know, a huge regional hub for national headquarters for corporations around here. And then second follow-up question is, you know, what types of bridges would you like to foster internally in UT Dallas, you know, either within other departments within natural science mathematics or within other schools within the university? Thanks.
Yeah, absolutely. So first question, sort of what collaborations would I seek out? Aside from maintaining my current collaborations, I would definitely want to reach out to the energy industry. I think there's a public perception that there's animosity there, but really the energy industry and scientists should be working together to sort of solve this problem. In my case of induced seismicity, because that's my subject, expertise. I would also reach out. I've been particularly interested in mining companies, especially with mining induced seismicity, which are complicated sources that are not well understood. And this is something I had started in Utah, collaborating with mining engineers, and it's something that I would want to continue. And in terms of, you know, on campus, I mean, my research sort of applies to everything. I would collaborate with the science teaching, I believe that Mary is a part of. I would absolutely love to do that. I would like to collaborate with the physics department and sort of, that's a sort of realm, I think, of theoretical seismology. And for my research particularly, we get at how is MLMC, changing this, because it's ultimately a mathematical problem. I would like to collaborate with social scientists and sort of how to incorporate DEGI into my research and into geoscience as a whole. And engineering, this is a collaboration that I had previously started, which is, engineers are dealing a lot, especially civil engineers are dealing a lot with soils and dealing a lot with, housing structures and things of that. And that is fundamentally a geoscience problem. And then lastly, the business school. I think it's incredibly important, things like insurance and thinking of our day-to-day lives and the protections that we have put in place. A lot of this has to do with business and it has to do with corporations. And not only that, but I think as professors, we are often we're in a management role, right? So it's helpful to understand how to most effectively manage and sort of work with business on how to maybe set up an academic management program or something of that nature.
Right. Salo, do we have another one from online?
Nope.
No. Oh, I think Ning had his hand up first.
Hello. So you mentioned there's a paper you published with others about the institution change using this DIV concept. I'm wondering what's the best practice of the example you have seen in those other geoscience department changes, and what's the most important part of where department can change into more like a DIV adapted department?
Yeah, that's an excellent question. So the question is an example of transformative resilience and I think how to incorporate that into a department. I would say the best example of transformative resilience was actually with my advisor, my PhD advisor. And it was sort of saying, this environment is not working for me, this department is not working for me, the city is not working for me. And he said, what do you need? And then he went and spoke to the dean and then created these changes for me. I'd love to get more specific, maybe outside of this forum. And then in terms of how to change the culture, that's actually a follow-up paper that we're trying to write. But it's you have to have, I would say the most important thing is you have to have the people in power, open and willing to change. Like that's the biggest thing, and that's actually one of the hardest things to achieve. And there's a lot of dissonance, I would say. Like there are a lot of people who have the ability and they want to, but they can't for whatever reasons, right? They're limited by the people above them and so on and so forth. And so I say, yeah, it's the hardest part is getting all of the people in power in this chain of power to all agree and to put their minds together and to adapt to the needs of students. And one example is climate surveys, right? Assess students, faculty, staff on the climate of your department, right? And then do something about it. Don't just collect the data and sit on it, but say, oh, this seems to be happening. Let's change this. This seems to be happening. Let's change this. This is an isolated incident. Let's address this and let's come up with maybe a reporting system so that these things don't happen again.
Right. I think
yeah. So you were talking about the potable water in Virginia and how they were re-injecting that into the aquifers. I was just curious if there was like a notable difference between the induced seismicity from that and then from like wastewater injection from hydraulic fracking.
That's a great question. So the question is if there's a difference between the induced seismicity from the municipal water management as opposed to wastewater injection. And the answer is we don't know. So the research well just came online in November. The seismic network was just installed in January, and they are not going to start injecting till May. So we're still in the phase of monitoring the background seismicity, of which there seems to be none. But I also think that there's an interesting situation there that makes it different from Dallas in the sense that they have a crater deformation under the water. And so they're really expecting to see that light up. And that's different because those are known mapped faults as opposed to a lot of other areas where, you know, you're like, oh, this is a reactivated fault that we weren't aware of. Yeah, it's a very good question, and it's one we hope to answer.
There's might be interesting. So I was in Southern California for 15, 20 years. There are massive treated water injection going on there.
Yes.
Because the water production is causing salt intrusion from the ocean.
Yep.
So that, and of course, Southern California is full of seismometers for other reasons. There might be some really interesting data to take a look at there on that subject.
Definitely. That's also what's happening in Chesapeake Bay. It's the saltwater intrusion. Yep.
Yeah. And of course, there's 40 million people, well, 20 million in Southern California, 25. Let's see, other questions? Anything online, Salo?
Nope.
No. Any other? Oh yeah, sorry, Bob.
So departmental climate questionnaires, is there a standard form and is there a standard procedure?
Yeah, so the question is there a standard form or procedure for the departmental climate surveys? So this is an interesting question. So we implemented this at University of Utah through our student organization, and there is a dissonance between what the social scientists want to ask versus what the department wants to ask. And there's also issues with small departments, an issue of anonymity. And so the standard procedure actually changes between departments and also between what people can honestly agree on. But there is social science literature to sort of say, you know, these are kind of the best practices, but you need to adapt them, right? Because of statistics of small numbers and
So we all have to come up with our own surveys.
yes, but the teaching schools and the social science schools, they've also already thought of it. So it's a lot easier to collaborate with them than to come up with it.
Well, it just seems like something that the DEGI initiative through organizations like AGU, the GSA, could come up with. We could adapt for our own purposes without going through pain and inventing the wheel.
Yeah, right now they're more focused on collecting demographic data. They're focusing on the legality and what questions to ask and how to answer. So I think they have it sitting on, you know, with AGU and SSA and all of that. Their focus hasn't gone this far.
Yeah, it's a good idea. Rich program review. We just out of interest, since you mentioned the climate surveys, we just completed a massive climate survey across campus a couple of months ago for faculty and staff. And the results are out. I sent around to everybody to record the slides and stuff. And it's pretty interesting. And a lot of it is focusing on the change through COVID, about what people's preferences are for how they want to work and things like that. And so those are being digested now. There is also other aspects too. We have a new, as of about a year ago, vice president of DEI.
Okay.
And I think
I'm
going to meet with her
Yep.
tomorrow. Yeah. So there's a lot of interesting things. The other thing is I've been talking to Charter Distance around and stuff about designing some 360 surveys. So we could do that kind of thing.
What is the
360 review means from all directions. So you're the people you report to, the people who report to you, and your peers. It's good to have a 360 and design it, you know, like maybe the new department head is not really your cup of tea or something, you could have, that could come out in a 360 survey. And it's also useful for the people or the groups or whatever, you know, whatever the issues are, to see what other people really think about them from all different directions, not just within your own niche or something. So HR is gearing up for this because I've been asking to, and others too, the past year or two, actually. I mean, pretty soon they're going to be ready to develop those kind of things on a, we could do it on a department basis, for example, and we could choose the issues that we wanted to illuminate and with them, and they'll work with third parties to deliver it and make sure it's anonymous and all that stuff. So it could be quite useful. Let's see, we're at our time, actually just a little bit over. Just because the online people are a little bit remote, I'll just check one more time. So do we have anything from online?
No more questions.
No more burning questions. Anybody got a burning question that they want to ask or want to personally be meeting with Monique through various ways, including student lunch right after this, after we wrap up here. Okay, well, let's thank Dr. Holt very much.